Hello and welcome to The Daily Space. I am your host, Dr. Pamela Gay,
And I'm your host, Eric Mattis.
and we are here to put science in your brain. In today's first story, we're going to call attention to the powerful role of computers in shaping our understanding of the universe, and in this case, in shaping our understanding of the shape of the universe. Since the beginning of the computer age, researchers have been trying to simulate how a universe made of a mostly smooth swarm of particles can over time evolve into the galaxies and large-scale structure that we see today. Early models started by simulating increasingly large numbers of particles of regular material, the kinds of baryonic matter that makes up us and everything we touch. Those simulations didn't work real well. Something was missing. Dark matter was added, and folks began fussing with how dark matter might be one temperature and regular matter another. And over time, models matched better and better. But the processing required got harder and harder since these two kinds of particles interact gravitationally, but not so much collisionally, and the software had to keep everything straight. Still, it was progress. But there was still stuff missing, neutrinos for instance. And that stuff interacts more like dark matter than regular matter, but is also constantly coming into and out of existence through formation in stars and destruction in rare interactions. These ghost particles, as they've been nicknamed, are in the universe tweaking its evolution. As explained by Project PI Naki Yoshido, these particle-based methods cannot accurately reproduce collisionless damping, a key process in which fast-moving neutrinos suppress the growth of structure in the universe. So, his team created a simulation that included neutrinos. A simulation that ran on up to 147,456 nodes of 7 million CPU cores. And their new universe in a digital box got that much closer to resembling the actual universe. What got me about this work is neutrinos aren't just hanging out in our normal XYZ plus time universe. Including them required solving what's called the Vlasov equation in 6 dimensions. Since our universe has at least 11 dimensions, models still will need to grow. But this is amazing progress. I can't wait to see what folks can create when we have quantum computers. From trying to understand how the structure of the universe has changed, we now turn to looking at how the structure of the land has changed over time. Our world's continents have always been on the move, and volcanic lands have risen up out of the sea only to sometimes be worn away with time and have sunk back into the water. We can see how the crust once fit together by looking at how fossils match on lands that no longer touch. Understanding the more islandy bits, that has been more of a challenge. But sometimes you get lucky. The boot of Italy is a seismically active region rife with volcanoes. If you want to go searching for old human relics, but not truly ancient relics, Italy is a good place to go. If you want dinosaur bones, go to Montana, or China, or other continental landscapes. It was thought that during the age of dinosaurs, modern Italy was nothing more than a series of islands incapable of supporting large dinosaurs. It turns out we were wrong. During a dig at the Villaggio del Pescatore site, University of Bologna researchers found multiple skeletons of the Taescheratus insularis dinosaur, as well as fossil remains of fish, crocodiles, flying reptiles, and crustaceans. These discoveries indicate that 80 million years ago, that land that became Italy was not only small islands that characterized the ancient Mediterranean, but many migratory routes for large terrestrial animals like the dinosaurs might have been possible across land bridges of what we now call Italy. A remarkably large part of science is just noticing that what you have isn't what you expect. Meteorites can do a really good job of pretending to be regular rocks, but they aren't. And when we can spot them for what they are, the science inside them allows us to get at information we could otherwise only get by sending spacecraft out to collect samples. While a lot of meteorites go uncollected, sometimes we get lucky, and the meteors are seen falling to Earth, and we can follow the fireball in the sky to the rocks on the ground. Such was the case with the Allende meteorite, which exploded over the Chihuahuan Desert in 1969 and scattered 2 tons of material across the landscape. This fragmented space rock is a mix of metals, minerals, and even glass beads that formed in the earliest days of our forming solar system. The structure of these beads reveals the conditions under which they were formed. And these beads describe violent collisions followed by rapid cooling at a rate of 500 degrees Celsius per hour. According to Nicholas Dupas, project principal investigator, one scenario that would fit this situation is massive shock waves passing through the early nebula. Large planetary bodies nearby can create shocks which would have heated and then cooled the dust as it passed through. These early shocks may be responsible for the loss of somewhat volatile elements like potassium and rubidium in the early Earth, where they don't exist in expected amounts. It turns out there's a lot to be learned from glass beads from space. After the break, we'll be back to look at our planet's oceans and the rocks that may have formed within them. Stay tuned. Meteorites are useful for answering all kinds of questions, including why is there so much water on Earth? One theory that has been gaining steam, so to speak, is that some of the liquid water we have on Earth comes from water-rich meteorites. But the isotopes didn't always match, particularly when it comes to water in the mantle and oceans. So perhaps some of our water is a result of our planet being bombarded by dust grains that came from asteroids and comets, where those dust grains contained water. And upon analyzing a different type of asteroid than the ones that gave us those water-rich meteorites, including Itokawa, which was sampled by JAXA's Hayabusa probe, researchers found water molecules that isotopically matched what we were missing. As scientists have worked to understand this process, a question remained about just how the water got into the dust grains. In a new paper in Nature Astronomy, a team led by Luke Daly has concluded that the water came from space weathering, where charged particles from the sun traveled through the solar system via the solar wind and altered the chemical composition of the original dust grains so that they now contained water. Daly explains further. Over time, the space weathering effect of the hydrogen ions can eject enough oxygen atoms from materials in the rock to create H2O, water, trapped within minerals on the asteroid. Crucially, this solar wind-derived water produced by the early solar system is isotopically light. That strongly suggests that fine-grained dust, buffeted by the solar wind and drawn into the forming Earth billions of years ago, could be the source of the missing reservoir of the planet's water. In simple terms, the solar wind is producing water under the surface of asteroids, and that water made it to Earth. Co-author John Bradley notes, since much of the dust throughout the solar nebula was inevitably irradiated prior to its accretion into larger objects, water produced by this mechanism is highly relevant to the origin of water in planetary systems and possibly the isotopic composition of Earth's oceans. And maybe we could use dust on other worlds like Ceres or Vesta or even the moon to process water straight from the surface. That's an interesting idea for in situ resource utilization, I think. Speaking of asteroids and comets, Astronomers are still working to understand that huge comet that was recently discovered and led Beth to yell at headline writers. Comet Bernadalli-Bernstein was discovered back in June of this year in data from the Dark Energy Survey, which has been working to survey the southern hemisphere sky. While most comets are about 1 kilometer across, this particular comet is estimated at 100 kilometers across, making it the largest comet ever discovered. Right now, Comet BB is out past the orbit of Uranus, but it's expected to come close to Saturn's orbit before heading back out toward the Kuiper Belt. So it's not a threat to Earth or even Saturn, but its size has made it an unusual subject of interest for planetary scientists. We've talked about the differences between an asteroid and a comet on the show and on Astronomy Cast before. But the basic point remains that they are essentially the same type of rocky body. Comets, however, are considered active when the ices in their structure begin to vaporize as they approach the sun and get warmer. These ices can be a variety of types: water, carbon dioxide, carbon monoxide, and more. Each type of ice vaporizes at a different temperature. And with Comet BB being so far away but still so large, astronomers led by Tony Farnham wondered if the comet was already active despite its distance. Unfortunately, the Dark Energy Survey images did not have the resolution necessary to say for certain one way or another if Comet BB is vaporizing. So the team turned to data gathered by NASA's TESS spacecraft. They stacked the images taken, confirmed their accuracy, and found that yes, Comet BB is surrounded by a hazy glow indicating the sublimation of ice. And due to the distance, the ice being sublimated is likely carbon monoxide. The results were published in the Planetary Science Journal. After the break, we'll be back to look at some strange new worlds. Stay tuned. Speaking of TESS, this mission continues to find the strange and different when it comes to exoplanets. A new paper was published in Science this week that details the discovery of a planet about the size of Mars called GJ 367b that orbits its star in a blistering 8 hours. So mark another one in your sub-Earth column and in your ultra-short period column, just in case you're counting. But wait, there's more. This relatively small world is close enough to its star that scientists could actually calculate its mass. And now we get to an even more interesting part. GJ 367b is a rocky world with a similar composition to Mercury and a solid core of iron and nickel, possibly making up as much as 86% of the interior. TESS observed the parent star's patch of sky back in 2019, with the planet showing up as a dip in the star's light. Astronomers confirmed the planet using the high-accuracy radial velocity planet searcher, HARPS, instrument at the European Southern Observatory's telescope in Chile. From there, the team analyzed all the data to calculate the various characteristics of GJ 367b. Mind you, this is not a habitable planet in the slightest. While the star is a red dwarf, the planet is still getting blasted by 500 times more radiation than the Earth gets from our sun. And with that close orbit, daytime temperatures are up around 1,500 degrees Celsius. However, it is very possible that this small world has a family, since red dwarf stars typically tend to have multi-planet systems. And some of those family members could be more habitable to life. And with the parent star being only 31 light years away from our solar system, this system is one to keep an eye, or rather a spacecraft's eye, upon. After the break, we're going to be back with a review of a new camera lens brought to you by our resident, camera aficionado, Eric. Stay tuned.
Another lens review this week, and it's one more for Canon's full-frame mirrorless RF mount. the Canon RF 600mm f11 super telephoto lens. One of my main interests is wildlife photography, which is why I bought one for myself a few months ago. Now, the first thing you may notice about this lens is the smaller aperture of f11. This really isn't a concern with modern digital sensors that perform well at higher ISO settings, such as those that you might need to use with a slower lens. The Canon RF 600mm f11 lens is intended for wildlife photographers on a budget. Weighing in at just 930 grams means you can leave the monopod at home. The lens has optical image stabilization, which has allowed me to shoot sharp images at 1/15th of a second, handheld. The autofocus is pretty fast. When taking pictures of birds, it tends to hunt for focus a lot before locking on, but I'm pretty sure that is because of user error and the limitations of the autofocus capabilities of my entry level Canon EOS RP, as I see this with other lenses. The lens has three switches on the side with separate focus and control rings. The switches control focus distance limiting, image stabilization, and focus mode. Like with all our system cameras, manual focus override is only available if you set the camera up right. If you grab the manual focus ring with autofocus set, it does nothing, since the manual focus ring is an encoder that tells the autofocus motor how much to move. A downside of the aperture is that you can only use about the center 80% of the frame with autofocus compared to all the way to the edge as with other lenses, an advantage of the mirrorless design. It's not that big of a deal, at least for me. Another feature of the RF 600mm f11 which I really like is its collapsible design. It gets about 8 centimeters shorter when collapsed, which is good for storage in a reasonably sized camera bag. There is a locking ring at the base of the lens that you must put in its closed position before using, but that becomes muscle memory after a while. It has a fixed 1/4 20 threaded hole for attaching a quick release blade for a monopod instead of a removable tripod shoe like on other more expensive super telephoto lenses. I don't use a monopod since this lens is stabilized, so I put a strap mounting plate on the thread. I learned early on that it's more comfortable to have cameras with large lenses facing backwards as you're walking, and that's mostly true with this lens, though the balance is a little off because half of it is a hollow tube. Image quality with the 600mm f11 is great. The diffractive optics design works. There isn't any visible distortion or chromatic aberration, and what small aberrations there are corrected automatically in camera. Because of the smaller aperture, you need to use higher ISOs to be able to use fast shutter speeds. I regularly use up to ISO 12,800 without a significant decrease in image quality. So I limit the ISO to that using the auto ISO setting. I'm really happy with the images I can make with it, given all of the advantages and compromises. Enthusiasts on a budget like me do not usually get this much focal length in a prime lens. Personally, I do not use teleconverters, but you can use one of the available RF teleconverters, what Canon calls extenders, with the 600mm f11 to obtain either 840mm at f16 or 1200mm at f22, using the 1.4 or 2x teleconverters respectively, though Canon notes that the lens might not autofocus at f22 using the 2x converter. Although Canon also makes a big brother to this lens, an 800mm f11, I decided to get the 600mm version, mainly because of its shorter minimum focus distance of 4.5 meters, compared to the 6 meters on the 800mm, which felt limiting to me because I might end up too close to the subject to focus and scare it off by when I have to back away. It stands, the first time I used this lens, I had to back up to get my subject in focus because I was closer than 4.5 meters. Another consideration was the size. The 800mm version is about 40% longer than the 600mm version, measuring at 281mm when retracted, compared to the 199mm of the 600mm lens. In addition to being smaller than the 800mm, I can use more affordable 82mm filters compared to the more expensive 95mm filters used by the 800mm lens. But the biggest consideration for me was the price. At $699 US, the 600mm f11 fit my budget compared to the $899 for the 800mm f11 model. This has been the Daily Space.
You can find more information on all our stories, including images, at dailyspace.org. As always, we're here thanks to the donations of people like you. If you like our content, please consider joining our Patreon at patreon.com/CosmoQuestX.